Okay, so far we learned how to implement this LUNET architecture. Okay, and LUNET architecture it was proposed in late 1980s. So their architecture is composed of convolutional layers and also the fully connected layers that we learned last time. So it's early CNN architectures, but if you see their architecture, then you can notice that their nonlinear functions are tangent hyperbolic, and also their pooling is average pooling they use. Okay, but tangent hyperbolic, if you remember correctly, it looks like this. Okay, and its x range is minus infinity to infinity, and their y range is minus 1 to plus 1. Okay. And similarly, this is the tangent hyperbolic function. And similarly, the sigmoid, if you see their functions, it looks like this. So here is 0.5. And their range, x range is same as tangent hyperbolic. It is defined for minus infinity to infinity, but their y range is bounded to 0 to 1. That's the sigmoid function. And if we, how to say, let's say this is the y, this is the y, and if we differentiate the, the output y respect to x, which is the input, for the tangent hyperbolic, then you can notify that their gradient means their slope in this graph. Okay, are you guys following this? Okay, so dy d theta, dy dx is defined as the slope in this x and y graph. Okay, but you can easily notify that for the tangent hyperbolic, uh, if x range is becoming larger than certain value or less than certain value, then their gradients are abruptly goes to 0. Okay? Are you guys capturing this? Okay. And similarly, in sigmoid functions, if x value is larger than certain value or less than certain value, then their slope is becoming too close to 0 abruptly. Okay. So because of this, when output of the deep neural networks are becoming bigger or becoming smaller, uh, because of, I mean, their subsequent modules are suffering to get sufficient amount of gradient because their slope is abruptly goes to close to 0. Okay, both in the tangent hyperbolic and sigmoid, this kind of phenomenon is observed. Okay, so one good thing in ReLU function is even though there are some discontinuity in here in this point, but there's I mean, exactly having 0 might be rare in neural networks. Okay, so anyways, uh, they, I mean, cannot model this range. I mean, if x is less than 0, they cannot effectively modeling this part. But I mean, despite this, they can well modeling the axis larger than 0 cases. Okay, so they are not their gradient, their slope, the differentiation of output with respect to the input is not vanishing. for the ReLU function. Okay. So you may remember that this is the ReLU function. Okay. So thanks to this, ReLU is successful nonlinear functions, becoming the successful nonlinear functions in the deep learning method. And because of these characteristics, later deep learning modules are not using these tangent hyperbolic or the sigmoid functions as their nonlinear functions. And also, um, rather than using the average pooling, that is actually blurring the responses. So if you average pixels with nearby values, that is actually blurring your responses. Okay. So rather than doing some blurring, normally we are nowadays pick the maximum values. Okay, by doing the max pooling. Okay. So among the values inside the window, we pick the maximum values to reduce the window size. So that's the max pooling, but average pooling, that was averaging the values inside the window previously. But it is somehow experimentally proven that max pooling is more informative than the average pooling for the image classification task. Okay. So sometimes we worry that if we choose only the maximum value and throwing all other values, then we worry that we are losing some information from the images. But yeah, in image processing, it is experimentally proven that throwing away non-maximum values sometimes helpful for achieving good accuracy. Okay, are you guys following that? Okay. So compared to the LUNET architectures that uses the tangent hyperbolic and average pooling, uh, the first successful CNN architecture, which is the AlexNet, they are using the ReLU functions for the first time. They use the ReLU function as the nonlinear function, and also the max pooling as the pooling operation. They first time used. Okay. And also the other techniques are used dropout and data augmentation. Uh, dropout means I will explain that here. So there you can see this is the overall implementation of the AlexNet. And I mean, roughly it works similarly uh, like previous one. Okay, so but if you see their detailed operations, then you can see now average pooling and tangent hyperbolic is replaced with max pooling and ReLU activation functions. Okay, and also here in the FC layer, you can see there are dropout layers. Okay, and what dropout layers does is for example, if you, let's say this is the, for example, one, 1024 dimensional of responses outputted from the previous deep architecture. And we may apply the MLP, I mean the linear layer, to map it to, for example, 412 dimensional vector, okay? By applying some, multiplying some weight and adding some bias, you are mapping this vector to the lower dimensional vector. Okay, that is the linear layer. But before doing this, right after doing this, what they do is they randomly removing some values. So this value may have some value like 12, I don't know, 34 and 102 maybe, but you randomly select certain number of node in the how to say, in the responses, one-dimensional responses, and make them in, zero. Okay, you delete some of the responses, but while retaining all others, you randomly select some portions of the output and make them zero, right? That is the dropout operation, okay? And what we do this is uh, by setting some of the output values to zero, you will not learn the weight for outputting these values, but you can focus on training the remaining, maybe, for example, for this node, if their values are not zeroed, maybe some inputs are connected to this node using some weight and bias, okay? And those variables are only focused to be learned during the training. And for the weight and bias connected to this deleted node will not be learned seriously during the trade, okay? So this dropout layer is actually helpful for training the robust model, okay? And also this selection, the output selection to be zeroed, is randomly selected every iteration during the training. So your model is becoming robust during the training, okay? And also this is helpful for avoid the overfitting phenomenon. This is the thing I mentioned in previous lecture. Overfitting means the model overly fits to the training data and it fails to achieve good accuracy for the testing data, unseen testing data, okay? So during the training, the data set we see, we iteratively see the training data, and there's no way to see the testing data in advance, okay? So without dropout, the model can be overly fitted to the training data, and their weight and bias that could be overfitted to the training data, okay? So resultantly, their weight could be less robust to the testing data, but if you use these dropout layers, then your model will not be overly tuned, cannot be overly tuned to the training data because all the connections are omitted during the training randomly. So involving some randomness in general helpful for making the model robust to the overfitting phenomenon. Okay, so dropout, that is the scheme added to make the model robust to the overfitting phenomenon. Okay, so that is the first thing, dropout. And the other thing is the ReLU and also use of the max pooling. That is the characteristic of this AlexNet, which is the first successful deep architecture. So in the year of 2012, previously that shallow learning algorithms such as the SVM perform best for the image classification task. Okay, but here, if there is some graphs, the x-axis, if they denote the 1980s, then there's also the LUNET architecture here. Okay. Okay, but here they only start from 2010, so there's no LUNET here. Okay. Anyways, I mean CNNs are the researchers tend to avoid this use of the CNN architecture for a while because they can be good for some simple tasks like digit classification, but if their data is becoming complex, then they tend to be overfitted to the training data and cannot be effectively trained. So their performance, as a result, their performance was not good. So researchers are not using that. Instead of using deep architectures, they try to use the shallow learning algorithm to get the, performance. But in the year of 2012, you can think like that. I mean, these type of things are helpful to prevent the overfitting phenomenon of the deep architectures. And you can now get the good generalization ability by preventing the overfitting. So now deep learning is actually working, and humans are becoming to know how to effectively training these deep architectures. That's the year of 2012. Okay, and another important thing is you have to remember is at this time in the year of 2012 they are using the GPUs. Okay, so you may now familiar that uh, I mean researching AIs requires a lot of GPUs, right? So actually, we need a lot of NVIDIA GPUs. Okay, so because their libraries are supporting deep learning algorithms, PyTorch is actually supporting NVIDIA GPUs only. So that's why we are all using NVIDIA GPUs now. Okay. Anyways, in the year of 2012, in the New Leaps paper, the author's name is Alex Krzyzewski. That's why we call this network as the AlexNet. Alex is a name and Krzyzewski is the last name. The first author's name is Alex Krzyzewski. Okay. I mean, here he first used the two GPUs when training this AlexNet for the ImageNet dataset, which is the largest scale image classification dataset. And it actually took 7 days a week to uh, get this performance. Okay, so he pay a lot of time to properly train this AlexNet for the ImageNet challenge. Okay, and this is the first architecture that recorded as the state of the art in ImageNet challenge using the deep learning architectures. Okay, and another important thing is you have to also remember many things here. Data augmentation, you may be familiar with this. Data augmentation means, I mean, this is the image of some human, for example. Then if you flip this human's image, left to right direction, maybe you can flip, maybe you can change left and right of this image, or you can apply some brightness adjustment algorithm on this image. Then even though some of the attributes of the images are changed, their class informations are same as before. For example, this is the human class, okay? Even though their brightness is adjusted, still this image is containing the human as, okay? And also, even though you flip the images in the left-right direction, that images still have the humans as the main object. Okay, so their semantic labels are not changed, but thing is, you can additionally use these brightness adjusted images as the additional sample, training sample, and also the images that is flipped can be another samples. So by applying this type of transformation in the image space, you can augment the number of images samples. Okay, so that's actually the data augmentation. So thing is, in the year of 2012, many things happened. So you can augment the data amount, and also you can use multiple GPUs that can support this large amount of data, and also the how to say this AlexNet also has the A layers, which is deeper compared to the LUNet architecture. Okay, you can now train uh, augmented data and also the larger architecture within a week. Okay, using the multi GPUs. Okay, that is important revolutions happened in the 2012. And also you involve in this architecture, we also involve some of the how to say layers, which is more robust for the training. Okay, like the ReLU, it replaces the tangent hyperbole and the sigmoid functions, and max pooling replaces the average pooling, and dropout is further used. Okay, so all of these techniques made this AlexNet successful. Okay, and yeah. So this is same definition of the AlexNet. Okay, roughly their algorithms are similar to previous. Okay, and next thing is the VGG network. I mean, this AlexNet was proposed by Alex Krzyzewski, but the supervisor was the Jeffrey Hinton in University of Toronto, and he actually won the Nobel Prize because of this. Okay, AlexNet, the first successful network for ImageNet classification. And VGGNet, that is the name of the lab in University of Oxford. And you can see AlexNet, compared to the AlexNet, VGG, their network is becoming deeper. Okay, so you can see their depths are becoming deeper, and they try to investigate the relationship between depths of the network and overall accuracy. Okay, so this is the deep architecture. So their motivation is if we make their depths deeper, their accuracy might be better. Okay, that's their motivation. And they stack mostly the 3 by 3 uh, convolutional layer, which means convolutional layers that uses the 3 by 3 filter kernels. Okay, so you can see in this figure 3 by 3. Maybe I'm not sure you can see. If you see this figure closely, their filters, the orange layers are all convolutional layers with 3 by 3 filter kernels. Okay, one box here denote the one layer. Okay, and blue box means the pooling layer, and green box, it means the fully connected layer. And this is the input, okay? And this is the final output, okay? So here, mostly there are convolutional layers with pooling layers, and here, fully connected layers appear. And this is the last layer. So this is the AlexNet having uh, 8 layers. VGG network, they are having multiple layers. I mean, actually, there are several variants in VGG having 11 layer to 19 layers. Okay, they define multiple layered architectures. And this is the code for implementing the VGG network. So you can see their kernel size is mostly the 3 by 3 kernels they are using. Okay. And here, of course, there are stride and padding is also defined. Okay. They first make multiple sub-blocks. Okay. Block 1 is also composed of convolutional layer and max pooling. Block 2 is also composed of convolutional layer and max pooling. This is also same. Fourth and fifth, they are also same. Okay. And then this is the last FC layer. Okay. Linear ReLU dropout, linear ReLU dropout. This is the fully connected layers. And you can see when X is inputted, which is the image, they are sequentially applying block 1 to block 5 and doing the flattening here and apply the FC layer and apply the softmax. Okay, this is the implementation of VGG, and their difference is only increasing the depth. Okay, are you guys following this? So, I mean, VGG network, using VGG network, you can, in this graph, you can see that this type of trend is appearing in the year of 2014. I mean, 1 or 2 years later, right after the AlexNet, most of the researchers are done using the deep architecture, but their trend is making them deeper. Okay, so here you can see the VGG network having 19 layers, and another important uh, architecture is proposed by Google, and they are called as Google LUNET, and having 22 layers, and having this is the error rate. Okay, 100 minus error rate is accuracy, so this would be their accuracy would be 92 something, and here their accuracy would be 93 something. Okay, anyways, there has been slight improvement in their accuracy. So this is the Google LUNET architecture. Okay, and you can see, Google. Firstly, their name was GoogleNet, but some researchers in Google found that their name can be LUNET. So after that, we call this as the Google LUNET, or sometimes we call it as the Inception network. Okay, because their basic blocks are Inception modules, so that looks like this. Compared to the AlexNet or VGG network, they are using some new modules called as the Inception module they made. And this paper is insisting that thanks to this Inception module, their architecture is becoming faster and efficient. Okay, so this is worth noting. Okay, so what this Inception module works is this is the previous layer's output, and they input this parallelly into the 4 different layers. The first layer is 1 by 1 convolution. This is the 3 by 3 convolution, and this is the 5 by 5 convolution, which means convolutions with 5 by 5 filter kernels. And this is the 3 by 3 max plane. And then they concatenate all the responses together, and this is the Inception module, which is the basic modules of this Google LUNET architecture. And you can see how this type of layers could be easily implemented in the PyTorch in the next slide. So here we will define some class whose name is Inception module. And this is the constructor for that, and this is the forward function. Okay. And here we will define 4 different layers we have just seen. Okay, that's the 1 by 1 convolution layer, and 3 by 3 convolutional layer, and 5 by 5 convolution layer, and the max pooling layer. Okay, we will define 4 different layers here, and in the forward function, we pass the initial x parallelly to these 4 different layers. And then what we do is concatenate them to make the final output, and we'll return the output. Okay, so this code is implementing actually this. Okay, are you guys following that? Okay, and then for constituting the overall Google LUNET architecture, uh, they are defining several layers. The first, second, third, fourth layers, but you can see, except for the first layer that have the convolution backspooling, the other layers are mostly composed of the Inception module that we just defined. Okay, and they are having max pooling at the end. Okay, are you guys following that? So layer 2 is having 2 of Inception modules and then max pooling. Layer 3 having 5 of Inception modules and then max pooling. 4 is also having 2 Inception module and average pooling. Okay, and here you can see they are sequentially applying layers that they defined and doing some flattening and applying the FC layer to get the final output. Okay, are you guys following that? Yeah, this is the LUNET architecture, and works slightly better than the VGG network. Okay, the important architectures are ResNet. Okay, so this is also proposed by Microsoft. Okay, and actually the first author of this paper is becoming the professor of MIT now, Kai-Ming He. Maybe you have heard about that. Actually, you can see here they are bounded to around 20 layers. Okay, I mean, they are wanting to increase the number of depths, a number of layers, which is the depths of the deep architecture. But the first AlexNet have only 8 layers, but later they try to increase the depths, but they are somehow bounded to the depths of 20, around 20 layers they are only having. But the researchers are wanting to further increase the depths of the layer, but they are when they try to achieve that, they meet some difficulty, which is this type of phenomenon. So this is showing the training error, and this is the training iteration, and also this is showing the training iteration over the testing error. Okay, I mean, uh, if we train more, this is the direction to take more time for the training, the model. Then training error should be reduced, okay? And also the testing error tend to reduce, okay? But the thing is, if we have only a layer model, like the AlexNet, the training, I mean, if the model is having less than 20 layers, if we stack more layers to that model, the both training error and the testing error is becoming too reduced, okay? Because this is the not accuracy but error, so the less is better, okay? From the 8 layer curve, I mean, maybe this would be 10 layer curve, okay? Until the model is having around 20 layers, if we stack more layers sequentially, then it works better, which means having less training and testing error, right? But the strange things happen when we stack more than 20 layers. If we stack more than 20 layers, for example, if we stack like 56 layer, then the accuracy, both testing and training accuracy is becoming less again, okay? So the researchers are becoming to uh, wonder why, okay? So this is the important phenomenon we have to notice. You have to remember this vanishing gradient phenomena. There are multiple reasons why the gradient vanishes. And I mean, the tangent hyperbolic and the use of tangent hyperbolic and sigmoid is also the reason for vanishing gradient, okay, which prevent the models to be properly learned during the training. But the stack of, I mean, increasement of the layers, more than 20 layers, that is also the critical reason to meet this vanishing gradient phenomenon. And after meeting this, the model is gradually reducing their accuracy. And I may have to explain why this happened. Okay. And this is the deep architecture. For example, having maybe 20 layers. Okay. And you may remember that the gradient descent rule, okay, that looks like this. Okay. So this is actually the gradient we have to calculate during the training. For all the parameter sector, we have to calculate this DLD sector, okay? But the thing is, for example, this is the first layer, and this is the loss function, okay? I mean, to calculate DL, the sector, for example, 1, and the parameter for the first layer, let's say it is the sector 1, okay? Then we have to calculate this DL, the sector 1, okay? But please, I mean, uh, please remind that how we calculate this DL, the sector 1. To calculate this, we use the chain rule. For example, this is the 20th layer. This is Y20. Their output, we will denote it as Y20 and their input as X20, okay? So we first calculate DL dy20 and dy20 to dy19, okay? And we have to multiply multiple gradient uh, to differentiate to, sorry, until we multiply dy1, the sector 1, we multiply this 20 times. Are you guys following this? Okay. So to calculate DL, the sector 1, which is the differentiation of the last loss, respect to the first layer's parameter, sector 1, we have to calculate multiple gradient, okay? And those gradient, have you thought about their scales, okay? Mostly their scales might be less than 1, okay? They will be mostly slightly or anyways less than 1, okay? And if you multiply some value which is less than 1, for example, 20 times, if we multiply the value which is less than 1 20 times, then their values are simply maybe goes to 0. Maybe the representation ability of the computer, maybe. If the values are too small, you will simply denote it as 0, maybe, okay? I mean, if you multiply some value which is less than 1 20 times, then their values are becoming too small, and the computer have to represent that as 0, right? Okay, because of this thing, if you stack more than 20 layers, even you stack more layers, this will happen more frequently, right? Are you guys following that? So because of that, this DL dissector cannot be represented stably, right? And it becomes just 0, and your parameters will be stayed, okay? Cannot properly represent their directions to update, okay? So because of that, after stacking more than 20 layers, their performance is becoming reduced again, okay? And that's why this ResNet has been proposed to solve this type of problem. And this is the normal deep learning architecture that sequentially stack the layers, okay? So this is the input X, and this is the convolutional layers, okay? And maybe we can represent, how to say, these two convolutions as the fx, okay? So this is the h of x, but in previous layers, that's just the fx. And f means uh, two convolutional layers and ReLU layers. If they are stacked, and then they can be represented as the fx, okay? I guess, okay, that's, yeah, just the definition, okay? But this is the residual network mainly used for the ResNet, okay? And what they does is, besides this main path, they are having additional paths that copy this input. And this is the new h of x now. So here, fx is retained, but you have another route to add the original input that is not fit to these fx functions, okay? And then if you differentiate this, maybe to the input x, the original input x, now the gradient looks like this, okay? And this could be some value which is less than 1, but you are adding 1 to that value, okay? So now the gradient are the values around the constant 1, okay? And because of this, even though you multiply this type of values more than 20 times, they are not simply vanishes to 0, okay? So because of that, adding this simple connection is helpful for retaining the stable training, okay, by removing the possibility of the vanishing gradient, okay. Are you guys following that? Okay. So this is why ResNet works. And actually, in the year of 2015, the ResNet achieves 3.6 error rate in image classification, especially for the ImageNet challenge. And that's actually better than the human performance in ImageNet classification. Okay. So, and that at that time, the ResNet is having 152 layers, and also they have also variant. As far as I remember, there are also 101 and 50, ResNet 50, ResNet 18. Yeah, this type of variants are there. So they are having some trade-off between speed and accuracy. Anyways, they are proposing multiple architectures. Okay. So so far, this is the ResNet comparison of the ResNet and VGG network. Okay. So sorry, this is This is the VGG 19 network having 19 layers, but this is the simple extension of the VGG network to have the 34 layers, okay? But this is the extension of VGG with the residual connections, okay? So this is not working, okay? Because due to the vanishing gradient phenomenon, but by introducing the residual connection, the training of this deeper architecture is becoming work. Okay, so we can get better accuracy by stacking more layers. That's the ResNet. And if you see this type of code, this is the code for implementing ResNet. So they are implementing multiple convolutional layers. But having different stride and also some have the uh, this is a different block, right? Yeah, this is different block, and having they are implementing that with different hyperparameters. Okay, and also they are implementing the bottleneck layers. The layer that I mentioned here is actually called as bottleneck layer because they add the residual connection. And you can now see they are mostly having the convolutional layers as the main path. And sometimes it can also have the downsampling. And depending on that, uh, they implement some variant for this bottleneck, having stride or depending on hyperparameters, having stride or downsampling, they are implementing different bottleneck layers here. Okay, but the main thing is this is the main passes output, which is the fx. Okay, and these two lines is implementing the fx. Okay, sequentially stacking layers, and those outputs you are adding the original input X. Okay, that's the implementation of the bottleneck blocks. Okay, So here you can see the original inputs are downsampled, and FX is applied here, and those downsampled inputs are added to the FX. Okay, that's the implementation of ResNet. Okay, I mean, if you implement this type of things without using PyTorch, you have to also consider the how to differentiate the gradient. But because you are implementing all of this using the PyTorch, you don't have to care about the backward. And many things are becoming convenient, okay, thanks to the PyTorch. And this is the overall architecture of the ResNet. So there are multiple bottleneck layers, okay? And yeah, similarly to previous ones, uh, except for the first layer having convolution, relu, max-spling, most of blocks are composed of the bottleneck layers, and they are simply feed forwarding this multiple times and then apply MLPs. Okay, that's the ResNet architecture. Okay. Are you guys understanding this, right? Okay, so that's for today, and also I will introduce something for. So this is another topic we have to deal with today. Okay. So far we learned reviewed the deep learning architecture and also the PyTorch, how to implement PyTorch. Okay. But we will return to the computer vision again. Okay. And previously I have explained about the segmentation task and also the pose estimation task. Also, we also learned about the object detection. Okay. So in this lecture, we will learn how we can implement the CNN architecture for tackling this segmentation and the pose estimation tasks. Okay. So in the segmentation, their output looks like this. Okay. So from the image, what we have to estimate is some pixel-wise class information we have to estimate. Okay. So here, I mean, we can know this is the human, and we have to get some masks for this human by inputting the RGB images to the deep architecture. Okay, that's what we wanting to achieve, okay, in computer vision. And also here in the pose estimation task, given this RGB image, we are wanting to estimate this type of skeletons, which means there are as I told before, there are 21 key points predefined in the human hand because we all know that human hands are having 5 fingers and 1 wrist. So we define 4 points for one per 1 finger and 1 point for wrist. So because there are 5 fingers and 5 fingers, they are having each 4 joints. So there are 21 joints. And here we estimate their XYZ coordinate value. Okay, that's the pose estimation task. Similarly, for the human body, we estimate, we also define this type of skeleton topology already, having mostly 20 key point and as point. Okay, we will tackling that. Okay, I mean, we can extend it further towards the mesh, which has more than 1,000 vertices, but that is actually heavy and also simple extension. So we will only tackle this skeleton representation. First thing is the semantic segmentation that I explained before. So given from this RGB image, we will estimate their pixel-wise responses. Okay, pixel-wise ground truth. We have to estimate. But naive way to achieve this semantic segmentation is we can apply the CNN architecture for these small patches extracted from the images. So for doing this, we can make some small sized patches which may contain like this amount of small sized window. And we actually apply sliding window approach for overall images using this small window. And for each window extracted, we can apply the CNN architecture that is trained for image classification task, okay, to classify what object is inside this patch. Okay, that is the most simplest way of implementing this semantic segmentation task. Okay, and indeed, in early computer vision papers, uh, especially when we use the shallow learning algorithms such as SVMs, we achieve the semantic segmentation in this way. Okay, we extract how to say the height multiplied by width time number of. Actually, there have to be this number of small patches. And for all of these patches, we apply our machine learning algorithm to classify that patches, okay, into semantic classes. That was actually the way we achieved the semantic segmentation before. But I mean, when using the deep learning method, uh, these deep layers are having many layers and taking a lot of resources to infer once. Okay, uh, it may take more than a few seconds, even for this small patch. Okay, and these patches are, I mean, one image is having this amount of patches. So because of that, when achieving the segmentation for an image, it may take few hours, okay, using deep architecture. In this way, it operates for the semantic segmentation. It may take few hours for achieving semantic segmentation for an image, okay? And it is impractical, right? And if it takes few hours for an image, it may be better to do this semantic segmentation by human hand, okay? It is impractical. So the computer vision researchers are thinking about how to make this efficient, okay? How to reduce the time taken for an image. So they are thinking of this type of architecture that is actually called as encoder-decoder architecture. And if they input this H by W by three-dimensional input, their output is H by W, okay? And I mean, and also you may remember that in CNNs, because of the characteristic of the max pooling and convolutional layers, we are tending to reduce the dimension, 2D dimension of the images into one-dimensional space, okay? You may remember that, okay? So we are doing the similar thing, and by applying convolutional layer and pooling, we are tending to reduce the dimension of the 2D images. But if we can, how to say, upsampling them again, and also can generate this type of two-dimensional output from the deep learning architecture. And if we are given multiple X and Y pairs, okay, and we can train entire architecture, deep architecture using these X and Y pairs, that will achieve this semantic segmentation task. Okay? That was actually the thing the computer vision researchers are thinking of. Okay? So previously, the CNN architecture are composed of only convolution, pooling, and nonlinear layers, and they are tending to reduce the number of uh, the 2D dimensions into the one-dimensional vector. But computer vision researchers are thinking of how to upsample these reduced vectors. Okay, but no, in general, upsampling is harder than reducing the dimension of the 2D signals. Okay, so I mean, thinking of this was not that trivial. Okay, and the answer is they are thinking of this transposed convolution operation. Okay, and it works in opposite way to convolution operation. So this is how the convolution works. Okay, so the blue pixels are indicating the input images, and gray pixels are indicating the filter corners, and green pixels are indicating the output images. So when filter corners are here, all of the pixels are pixel coefficients element of the filter coefficients are multiplied with all pixels inside the blue images, and they are added together to get one output pixels. And then the windows are shifted and do the same for getting all the pixels in the output images. Okay, that's how the convolution works. Okay, and they are composed of mostly the addition and multiplication, so their output is differentiable respect to the input, and they can be usable in the deep architecture. But the transpose convolution operation works similarly to the convolution operation, but the thing is they are tending to increasing the dimension of the output compared to the input. Okay, so for example, here, their input is 5 by 5, and their output is again 5 by 5 in convolutions, but here, their input size is 2 by 2, but their output is becoming larger than previous, okay? But what they work is same. When this is the gray windows is also denoting the filter corners of each coefficients are multiplied with the input image pixels and added together to get the output, one output pixels. That's same, and that is also composed of plus and multiplication and differentiable, can be usable in the deep architecture. But this type of characteristics happen due to the attribute that will be introduced shortly. Okay, so this is more slide for how this transpose convolution works. Okay, so for example, this is the 5 by 5 dimensional input image, and this is the 2 by 2 filter corner, and we will use tried one. Then in the transpose convolution, we by default apply one zero padding around the images. So this pink colors are input images, okay? And by default, when doing transpose convolution, we by default apply one zero padding and apply the convolution operation to get the output image. So because we are applying by default one zero padding before doing the convolution, the input images are 5 by 5, but the output images are becoming slightly larger. And also, the other thing is when we use stride as 2, previously, if we use stride, if we set stride larger than 1, we are tending to, in convolutions, we are tending to reduce the dimension of output heft, okay? I mean, if we use the stride 2, then the output size will be halved, okay? But here, if we use stride 2, then actually what we do here is this is the input, but we are rearranging the input pixels in this way, okay? So we are actually rearranging the images to have some offsets between the original pixels, okay? And then apply 1-0 padding around the image, and then apply convolution operation to get the output image, okay? Are you guys following this? Okay. So because of that, you can feel that input dimension is 3 by 3, but the output dimension is now becoming larger and larger, okay? They are actually doing some upsampling. And also, this is also different opposite way to convolution operation. So if you use more than more than 1-0 padding, uh, zero padding in transpose convolution is actually reducing the dimension of output opposite to the convolutions. In convolutions, if we use zero padding, then it is increasing the dimension of the output. But in transpose convolution, actually, it removes, if we set zero padding as 1, it removes the padding by 1 pixels, okay? So the padding is also having opposite meaning to that of the convolution operation. So actually, this is how the transpose convolution works, okay? And I will only deliver the conclusions today. And the conclusion is, I mean, this is when constituting some deep architecture for this semantic segmentation, original CNN operations are tending to reduce the dimension of 2D signals. But if we constitute the later deep architectures with the transposed convolution operation, we can actually upsampling the output, okay? And then we can eventually make the same dimensional output signals to the input signal, okay? And also you can also notify that this transposed convolution is a differentiable operation and can be usable in the deep architecture. And this is actually the code for implementing this encoder-decoder architecture. The first part is called as encoder part, and this part is called as decoder part. Encoder is, in general, meaning the process of extracting some one-dimensional feature. So you are extracting some feature, and in the later part, you are expanding that to the image space again. So here we implement the encoder network using the stack of convolutions and nonlinear layers, but decoder, you can think the transpose convolution and nonlinear functions are used to making the decoder part. And here you can implement encoder-decoder by sequentially feeding your input X to encoder and decoder, okay? And this is the encoder-decoder architecture. And using this type of training code, you can train this encoder-decoder to the semantic segmentation task if you are given many X and Y pairs, okay? And also the same network, same encoder-decoder architecture, I mean, you can now generate some output which is same dimension as the original input. The researchers are thinking of generating images itself rather than the segmentation masks. Okay, so now the same architecture, encoder-decoder, having transpose convolutions can be usable for generating images. and we will learn further later. And later we will also learn about how we can implement post estimator. Okay. Okay, so for today, I think we can finish here and maybe we can see next Monday. Okay, thank you.